All right. So we'll get started with our plan for the day. So the
Yeah.
plan is going to be that we'll go through a mock interview in the first good chunk of the time, and then afterwards we'll give you some time to hear some feedback from me, as well as for you to ask any questions you have about the problem or the process. Does that sound good?
Yeah, that sounds good.
All right. So you can pick a language of your choice.
Okay, so I'll pick Java.
Great. So I'm going to paste the problem that we'll be working on at the top here, so you can take a moment to read this.
Okay, so we have been given a list of words and we have to navigate through the matrix to form that word. And we are not allowed to go diagonally, so it could be only horizontally and vertically, right?
Yes, that's correct.
And we can only use the word once. The letter once.
So the letter from the same index or the same spot only once. But
yeah.
Mhm.
Got it. In this case, we have MI and I. But in this case, then how is it forming minis? Because you have MI
So we have the M here, and then
Yeah.
I.
Oh, like that. Okay.
I, S.
Okay. Yeah, the other way would not work. If you navigate to the other eye, then it won't work. Okay, got it.
Exactly. So I put that case deliberately in there just to kind of help you see that in case.
Yeah. And then can we assume that there would always be a valid word?
No, if not, you just return empty.
Okay, got it. And then we can assume all the letters are small case, or is there any kind of restriction on what could be the input, or it could be any?
Yeah, that's a good question. Yeah, let's assume that it'll be just lowercase alphabets.
Got it. Okay. So I think the first thought that comes to my mind is to just have this input list converted into a set. So that makes our lookup easier. And then from the matrix, you can just do DFS to kind of navigate your way through. And you want to begin with each letter because you can start forming a word from every letter. And then you want to go in all four directions. And you also want to make sure that you don't get into an infinite recursion. So you want to keep a track of what you have visited, right?
Mm-hmm.
And then since you said that it could be only small case characters, maybe we could swap that letter with something else, like a capital case or a special character, and then swap it back so we know it's visited. Yeah. And then we just keep forming the word and just checking it in our set.
Yeah, that seems like a good approach to me.
Okay. Then shall I start coding?
Yeah. Let's go ahead and do it.
So I've got this class. You can see me typing, right?
Yep.
Okay. You want to return a list of words or a so if a word is repeated more than once, we want to return it how many times it has been found, or we just want to return, we want to return the set. Okay. So I can, and then I have this set of string, that's my input. Actually, sorry, this is a list. And I have a matrix, which is a I think the first thing I want to do is now convert this input into a set. So that would be, I think I could do this. And then I want to go through that matrix. And it's not necessary, it's a symmetrical matrix, right?
The what, the matrix?
It's not symmetrical, like it's not n by n, or the rows and columns could differ, right?
It is. If you look at line 9 there, it says given an n by n matrix.
Okay. I think this would be safe, just in case. Okay, and then so I will write my DFS function, and then that function I will call from here, and that would be the initial character. Now the return type of that DFS should be, again, a set of strings, because it is possible that you're starting with a letter and you keep continuing. You found a word, but you want to keep continuing with that sequence. So my DFS should look something like this. And I also need the set. And yeah, I think that's it, yeah. And then you want to check, maybe I could make this, let me see. Yeah, let me make this void so we can just add. So we would check for out of index first, out of bounds for any of the indexes. So I less than 0, I matrix.length, or j is less than 0. Or j is matrix.length, or the character we have is already visited. So in that case, it's not a lowercase. So, in this case, we could just return and break from that recursion. Um, and we also want to keep a track of the word which we have formed so far. So on each recursion, we are adding to the word that we just appended. So word so far. And what we want to check is if the set input set has that word, we want to add it to our output. And then we also want to make sure that we toggle the characters, so maybe make it something else other than lowercase. So maybe something like just a random capital letter. And then you want to recurse in all directions. And then you want to add the character like this, and the input, output. Yeah, I'm missing something. Which so far, okay, yes. And then we want to toggle back the, because we want that matrix to go back to its original state. This, and then we can call this from over here, and we can add it to our result. Input is in, and then well, I mean, we are adding it a void function, so let's do this. And then we can add temp result and this overall result. Yeah, I mean, this should work. Should I run this?
Yeah. So we won't actually run it. We'll just kind of talk through it.
Okay. Okay.
Do you want to just kind of like run through an example? It's kind of hard because there's many recursions happening, but maybe we could just try the examples that we have and try for a certain case and just kind of walk through each line to make sure we're on the same page here.
Yeah, sure. So let me change this a little bit just to make it easier. We can walk through a simpler example, or maybe do something like this. So we're looking for one word, LOL. That's a valid word. So, and maybe we can start somewhere else. Like this. So we would start with the first letter, and then we would call our DFS. And the first thing we are checking is index out of bounds. And we are also checking if that's just a lowercase character or not, just to make sure we are not in an infinite recursion and we're not visiting what we have already visited. If the input, and then we are also forming the word we have obtained so far. So in this case, so I'm guessing here's a bug. So we want to, well, I mean, I guess this is fine because you're just checking for blank condition, like a blank string in the first case. So I think it's fine. So you don't have an empty string, so that's fine. And then you would recurse in all directions. So you would go up, that would be index out of bound. You would go left, that would also be index out of bound. You would go down and right. So on the third one, you would get A because you have not added it. So now in the next recursion, it's just A. But you would continue this path, and then you would have A and L, and so on. And you're checking basically that the word you have formed so far exists in this set. And if it doesn't exist, you want to still keep continuing because it might have it later. Am I explaining this right, or like should I explain it?
Yeah, I'm following you there.
Okay.
I'm following you there.
Okay.
So I think we kind of give that a path. It's not going to lead anywhere because we don't have any words starting with A.
Yeah.
So let's kind of go to a case where we do have an answer.
Okay. So the answer we have is starting from the last letter, which is L. So in the first recursion, you have a blank value, and then you would go again, and you would add this value, L, and then you would go L, and that path would not yield a result. You would go LO, and then LOL, and that would give you a result. And once you have that result, you want to add it to the output, but you don't want to stop because it is possible that you have LOL and then you have LOL something else. So you keep traversing until every letter is traversed, and in the end, you're adding it to your output, and then in the end, you're also restoring what you changed because you want it ready for the next iteration from here.
Mm-hmm.
Yeah.
Okay, this looks good to me. What is the runtime of this?
I would say the runtime complexity would be the size of this matrix, so m cross n, and that would be the size of matrix because we're traversing the entire matrix. But internally, we are also dependent on this set, but look up for within the set, I believe, is constant time. So we can ignore that.
So are you saying the runtime would be n squared?
Yeah, I mean size of the array. So yeah, if the n squared, where n is the size of the number of rows or number of columns, yes.
So if you look at line 54 and 55, so that's where we're kind of traversing the entire array, right?
Yes.
So for each element in the matrix, we run a DFS. So then that would mean that DFS is running in constant time, right? If it's true that it's n squared is the runtime.
Can you repeat the last part again?
So if the runtime was n squared, that means that everything inside this loop has to run in constant time, which would imply the matrix in the DFS, but that's not quite true, right? We actually do multiple traversals that I don't think is bounded by constant time. For example, let's go to line 15 through 19. Like when we're searching for that word minis here, like we go through this path, this path, this path, this path, and then we kind of say, okay, we're done, but we haven't formed a word. Yeah. When we come across this path, we form the word here, this path right here. But in traversing just those two paths, we've ran across these I and I's already twice, right? Yeah. So we could already tell that it's going to traverse the matrix more than a constant number of times. Correct. And so, and I guess from every letter you could go in 4 directions. And I mean, that's not true for every letter, but at most you would go in 4 directions. And then you would do that for every letter. So that would be 4 raised to the power n if we want to take the bigger complexity. Okay. So what would the final runtime be if you can just write that down somewhere? Yeah. So would be n squared. And this is like to the power, so 4 to the power n into n. Cool. Yeah. So yeah, I think this would be the way we can bound the runtime. I think we can actually get this to be 4 to the power of n though, because if you like pick any one direction, the furthest direction that you can go to is n. Right, because right. You're unidirectionally going in that direction. Yeah, that's right. Yep. All right. So I think this looks pretty good to me. What are some ways we could improve the runtime of this? Yeah. So I would definitely think about not traversing the entire entire matrix from every letter, because if you could understand how the words are beginning, you don't have to necessarily go through that path. So you could, instead of doing an actual comparison, you could do starts with, and if you see that, for example, there's nothing that starts with A in this set, then you don't necessarily have to traverse that entire path. I'm thinking we could do something with tries where, so if you build a try out of this, yeah, I think we could use tries where we're building a try with this, right? And then
with every letter, you could say, I'm gonna navigate in my try whether it starts with this letter or not.
Mm-hmm.
Yeah, so that could be done. I think that would be more optimal. Yeah.
Mm-hmm. What does that help with? Like, what does that help you do besides identifying like, whether that element in the matrix you want to traverse or not? What else does it help with?
So, so when you're building that try, on every letter you could have a word which can be formed starting with that letter. So you always know ahead of time if the word I'm looking for will be formed with this letter or not. So you don't necessarily have to traverse the entire path. You can tell at every letter what are the words this letter will be. What are the words this letter can be used to form. So, for example, yeah.
Yeah, so it'll help you prune quite a bit when you're going
Right.
down that. You can stop traversing down so many pathways, hoping that it'll form a word eventually, but you could kind of
Right.
predetermine, yeah, this is not going to lead anywhere.
Yeah, exactly.
Okay, sounds good. All right, so I'm actually going to put a different problem that we'll be working on line 89 here. So you can also take a look at that.